Good afternoon, everyone. Welcome to our CyLab seminar series. Today we have Pei Zhang from our Silicon Valley campus who will discuss his SensorFly work. Pei is an assistant research professor in the I&I and ECE departments here at CMU. He received his bachelor's degree with honors from California Institute of Technology in 2002 and his PhD in electrical engineering from Princeton in 2008. While at Princeton, he developed the ZebraNet system, which is used to track zebras in Kenya. It was the first deployed wireless ad hoc mobile sensor network. Currently, his work includes SensorFly, which focuses on swarm of autonomous miniature helicopter-based sensor nodes. His primary research interest is in easing setup and functionality of ubiquitous embedded systems through intra-system collaboration. Please welcome Pei Zhang.
Okay, can everybody hear me? Cool. So yeah, I'll be talking about the SensorFly thing. But before I get to that, I sort of have to get through like a small overview of this area, I guess. So, you know, sensor network really came not too much earlier. So there's about a decade worth of research in here. Maybe a little more. So it started out with some Great Duck Island stuff where people were trying to measure temperature in nests, volcano stuff, measuring vibration near volcanoes, a bunch of sensors everywhere. But most of them were pretty fixed, things that didn't move around. And then slowly research moved to things, well, what happens when things gets moving? And so we decided, well, let's put some sensors on the animals. So there were ZebraNet, TurtleNet, DeerNet, DuckNet, whatever Q animal /net you can think of. So this talk will sort of look at these large-scale sensing, things that we call ZebraNet, and then move down to some of the more building-scale sensing, things we call SensorFly, and some of the challenges and the work related in that area. So let's begin with zebras. Why zebras? Oh, I can use this little thing. Why zebras? Well, for us, we don't really care about zebras. We're computer scientists. But for the biologists, they're actually quite interesting. For one thing, they want to know the interactions within a species. Who likes who? How do they interact? Things like that. How do interspecies interact? For example, the lions, do they chase the zebras away, or does the zebras lead the lions away? And perhaps what's more important is this human-animal interaction. For example, how does animals migrate? If I fence off this watering hole, would that make the zebra die? If I don't fence off, would that make the farmer's cow be very thirsty? So it's more like a land management thing that they need to figure out. So for the biologists, it's actually not a very simple problem. So to track zebra, what they do is they go out, they take their binoculars, look at zebras, they drive around using VHF collars. They put a collar on the zebra that goes beep, beep, and they point that antenna around, and then they hear, oh, the beep is strongest in this area. Let me drive toward that. And then they get off the car again, and then, okay, now it's over there now, so drive toward there. So it's a very time-consuming thing. So so perhaps once a day, they can get one zebra fix through visual verification. And once they see the zebra, they will look at their behind, see all the stripes and everything to identify the zebra. It's sort of like a fingerprint. So just imagine a bunch of biologists looking at zebra behinds. That's basically what they do all day. But we thought that and say, well, is there a better way we can do these things? So we thought, well, maybe sensor network would be a good way to do this. For example, we can do this without infrastructure, something that's really lacking in parts of Africa where zebras roam. We can form a network and move data around. And it's unobtrusive, it's really small, so zebras probably don't care. So a classic sensor network is something like this. You have a sensor with some type of radio range. But of course, one device have a really short range, so it can't get data anywhere. So what you need is lots and lots of devices. So the major problem is that you need a lot of devices. That means you need to deploy a lot of them. That means the deployment cost is going to be really high, and your coverage area is going to be really limited. And just the fact that each one of these things have a battery is really going to pollute the environment you store these things around in. So we thought, well, what if we attach these things to the animals, just like a mobile phone? Well, and then the animals, when they get close to the destination, the cell phone towers, they can just upload the data. Well, the good thing is now nodes can be mobile, and they're not limited by where we deploy our nodes. But the problem is now we need a high density of base stations. Now, it may be fine in cities, but zebras tend not to wander into cities. And in the wild, well, cell phone companies tend not to build towers for zebras. So that kind of put a damper on things. So we finally thought, well, maybe we can use a collaborative method to pass on the data. So when two zebras wander close to each other, they can exchange data. And when two other zebras wander, they can exchange data. And finally, when perhaps one zebra coming to the base station, they can upload all their data. Anyways, yes, they can upload all their data. So one of the most major things we figured out was actually this energy problem. You have a limited amount of energy. So our most focus was on how to reduce energy. Well, a lot of these animals, they probably don't care. If you're talking about an elephant, well, you can put a battery, you can put a car battery on them. In fact, that's what people do. Right? You imagine a car battery next to an elephant. Well, it's really not that big, so they don't really care. But for zebras, that's going to be a slight problem. So a lot of our research focused on the energy reduction side of the thing. So we build a hardware that is 96% efficient, blah, 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 blah. There's also protocol research that schedules sleep, that determine how to do low energy software updates, data compression to reduce energy, probabilistic localization to reduce the GPS energy. And there's a bunch of papers on that if you're interested in. But all these are just theoretical work, and nobody really believes in theoretical work. So how do we actually have a test bed to prove this? Well, to prove this, we actually went to Kenya and shot ourselves some zebras. That was fun. So this is a zebra with a little dart of, opium on them. So this is your zebra. This is your zebra on opium. We put a color on them. We get them a little antidote, and they start running around with wonderful neckwear. So we actually deployed this thing twice in this place called Sweetwater's Ranch in Kenya. It's a place about 10 kilometers by 10 kilometers. We put a base station right near the visitor center because we're pretty lazy and don't want to move around. And we have a Yagi antenna that's directional that covers this area, which covers 1, 2, 3 watering holes. These are places where zebra come to drink. So our hope is to capture some of the data when they're drinking. And this is data from 4 animals. So we tagged this on 4 animals, 2 female, head of the harem, 2 head of a harem female. So in zebra society, it's matriarchal. So the female of the family leads everybody around. So 2 are female head of the family. 1 is a bachelor male, and 1 is a young female, children. So it's actually pretty interesting what you can see just from the biologist's point of view. What you see here is that the blue and black are the 2 head of the family, what you see is that most of the data is concentrated on really plains area, right between the quote-unquote rivers. So what that means is that they're spending most of their time on the plains eating grass, and that's sort of expected, right? They're herding the family, so most of the time they're eating. So the green one you see here is actually the bachelor male. So what they do is they don't have a family, so you see that their data is all over the place. So they're actually, if you see the time aggregated data, they're actually jumping around from the plains to the plains. So basically they're looking around, they're looking at where all the other zebras are, checking out the girls, going to parties, that kind of stuff. And you have this little children here that's following the family that's down here. That sort of follows the family wherever they go. Yeah, not as exciting. So yeah, anyways. So basically we have deployed, on the second deployment, we only have 4 nodes. We got many peer-to-peer link, a lot of fixes. So that was nice and all. And we also have sort of some impact in the area. For example, in developing regions, air projects use delay-tolerant collaboration, similar to what we have, to enable sort of woman's voice in the community radio. So basically, in places in Kenya, the women's work the field, so they weren't able to have their voice in the community radios, and this allowed them to record their program while they're working in the fields. In the United Village project, they use store and forward to give people local internet access. So basically, you type a Google search, this Google search query hop on a bus, go to the city, and in the city, you hop to the internet, come down from the internet with all your Google searches. So 2 days later, you will get your results. But that's still better than nothing. And of course, there's a bunch of sensor network that came after us, 200 plus projects in the polar regions alone, all those Q animal nets. But this work has been a little more than 5 years. So what does it mean in today's time when perhaps everything is dual core, quad core, things like that? So there are a couple of lessons what we take away from the ZebraNet project. Especially that, the deployment is all nice and all. It's a first mobile deployment. We learned that dynamic delay-tolerant networking can actually estimate system parameters, and we can really adapt to a lot of motion that the animal had. But really adapting to zebras are really a pain in the butt. So is there any way that we can get rid of this adapting to motion and have the motion adapt to us? So what if we can control some of these motion? Can it make our life easier? Well, this has been done a little bit too. So in Australia, there's this project using delay-tolerant network on cows to track where they are. They have like huge hundreds of kilometer by hundreds of kilometer places, farms, where the cows just roam freely. So they want to know where the cows are. But sometimes they also want the cows to come back. So they needed to control some of their motion. So what they did was they built a collar just like the zebra collars with one little addition, I guess 2 little additions, little electrodes on the side of the neck. So what they do is that if they want the cows to turn right, the left electrode will go bzz, and the cows get electrocuted and turn right. And if they want to turn left, vice versa. So actually, the paper is quite interesting. If you actually read it, they spend like 2 pages saying why this is humane and that doesn't kill the animal. But the idea is still out there. So basically, we're moving to where we had before was sensing and networking, sensor networks. And then we're slowly moving toward more actuation. So this cyber physical system idea. Once we do sensing, networking, and once we actuate, what can we do with these things? So this brings us to the next part of the talk, more of a building level sensing, the SensorFly stuff. The stuff I'm doing now, all more exciting. So the idea here is that what if we can control the motion? And this target application is things like emergency response or police and urban combat type of things. Places where you really don't want to be. Right? For like traditional sensor network, usually what we require is some poor graduate student go into these places and deploy the system. And that's probably not a good way to deploy this type of system, because these things are dangerous. And there are places that people even can't get into. The dangerous, very dynamic places. For example, right after the earthquake, we really needed to know the radiation pattern inside the building for the Japanese nuclear power plants. But people just cannot go in there. So what do we do? Well, our solution is this, what if we put wings on sensor nodes? Well, this is sort of what we got.
I am Pei Zhang. I am an assistant research professor at Carnegie Mellon University. I work on sensor networks. I'm developing a mobile sensor swarm that's called SensorFly.
Call this a superhero shot.
We're building small helicopters that can go into a building in a huge swarm.
One of my students.
The helicopters themselves have radios that can talk to each other and measure the distance between helicopters. And they also have gyroscopes that can measure how they turn, compasses measure which direction they're facing, and accelerometers to measure if they hit a wall or not. They can fly together into a building in groups. Some will land and provide instructions for the other helicopters. Some will keep on flying and look around to see if there's anybody around. We plan to use SensorFly in emergency situations. If there's a fire going on, the first thing to do is probably not to enter the building. But you do want to enter the building if there's a person trapped inside. So what do? Well, you send these helicopters in to look around first. If they discover somebody, then you send in the rescuers. So we don't have to needlessly risk lives of rescuers. So SensorFly will tell you where to go. And on your cell phone, you will basically see an arrow that will tell you which way to travel, which doors to go through, which direction you should take the next step, and then eventually reach that particular person. Although we have a couple helicopters right now, we plan to have eventually up to 100 helicopters exploring one building very quickly.
I love professionally made videos. They're so much better than what I can do. But, okay, so some of the first question will be, well, isn't this just a little robot that's been done before? Well, so there's one huge difference considering most robotics type platforms. I think the lowest weight platform that's currently out there is somewhere about 1 kilogram in weight. That's because for a robot, there's a lot of sensors on there. So, unfortunately, the weight just goes up. So what does that mean? That means you need bigger, well, that means, well, it's heavier, so the blades spin faster, right? So you have a really fast spinning, very sharp blade that's coming towards you inside the building. So that's not the exactly safest thing to do. So our platform is, reduce a lot of things, and we got a 30-gram hardware that's only based on off-the-shelf components. So that's sort of the reason why we can get low weight is because we really cut down the number of sensors. So cutting down the sensors means reduce weight. Reduce weight means reduce cost. Reduce cost means we can have more numbers in real deployments, and which means that if we have more numbers collaborating, we can further reduce the sensors. So that's actually a nice little circular thing. The idea here is that instead of a huge robot that sort of is a bottleneck for things that goes exploring. So usually when you have a sort of emergency situation that with somebody inside, the police, what they do now is send in this particular robot. I think it's $20,000 or something. So in fact, a couple of days ago, they, I think it was about 6 months ago, near Sacramento, they had actually police held up somebody was inside the building, a little crazy person, held himself up inside the building. And because they didn't want to risk police officer's life, this police officer from Roosevelt, I believe, Roseville or something like that, sending in one of these robots. And this guy just got so pissed off. It's like, how dare you intrude when I'm trying to barricade myself? So immediately what he did was he used a baseball bat and broke the camera. So of course, then they lose all situational awareness. The guy set fire to everything, including the robot, and they lost a couple $1 million worth of property damage. So instead of one point of failure, what if we can have a bunch of these devices? So these devices you can send in, well, the guy can use a baseball bat, swat at it for a long time before he can destroy most of the system. So these things will somewhat land and provide information for the flying nodes. The flying nodes will look around for interesting things. And these data will be passed back to the firefighter or police officers outside. Because it's a sort of a new system, there's an array of different research that sort of goes on at my lab trying to figure out how these things work. One thing is we build a minimalistic hardware. There's minimalistic control on top of that. We need to localize these things on top of that, and they need to form a network. And in that network, they need to plan tasks and provide coverage. And there's also applications, of course. So the minimal hardware first. This is a current version of hardware. I'm actually working on the newer version, so next time perhaps there'll be something new here. What it is you get the standard, like the 9-axis sensors. These things all feed into a little ARM processor, fairly slow by today's standards. You get 2 motors, ultra-wideband radio for communications, and a small battery. And these things are fairly reliable. Sorry, my students made these. They have terrible taste in music. But this is sort of the system. The idea is that we want to minimalistic everything, so you barely have any sensors. In fact, this is one device flying. It's trying to hover with aid of a high sensor. You see it drops because the high sensor gives errors. So it's trying to handle all these errors. It's constantly flying forward because I didn't want the added weight of the tail rotor. So to hover in place, it just spins. It's hovering by robotic standards. This is a terrible feedback loop. It's hovering up and down, up and down. But for human-sized things, these are actually good enough, so it can fly indoors. And with the aid of a couple of devices on the corner of the walls there, it can actually localize itself using its radio and determine relative path. I'll get into more of that in a few later slides. Because it's a little light, it can actually sense the wall by hitting it. And you rarely see this on robotics videos. So these are sensor networks. So it's actually really light, really robust. So you can actually do a lot of things that perhaps standard systems don't really consider. So failure is definitely an option here. Okay, anyways. But to do everything, we really need localization. So I'm going to talk about localization for the rest of my talk. And localization is not just for SensorFlies. Even in the office environment, haha, no, okay. Anyways, but in the office environment, there's a bunch of devices and mobile phones, printers, and thermometers. And what would be great is that these things can know the relative orientation of each other too. So if they have fine-grained localization information, we can have a bunch of ubiquitous computing applications too. So for example, if you have an office, and you have a mobile phone with the pictures on there, and you can swipe your finger to the printer, to the physical location of the printer, and it gets printed. Or in the other office environment, if you want to pass a file around, you can physically drag it towards your location. right? So these physical interactions doesn't exist today because of lack of quote-unquote localization information. Content sharing, of course, SensorFly. So what we really need for at least SensorFly purposes is a two-tier approach. We need to figure out where the anchors are using radial compass, a very broad type of thing, but we really need fine-scale location. So all these applications need these fine-scale location. So what do we need? Well, we need to determine this relative physical arrangement of a bunch of network devices. We need accurate, we need really high accuracy, sub-meter by high accuracy, something to the human size, right? We need to work on off-the-shelf components, off-the-shelf devices. That, it's cheaper that way. But it'll be nice if it's non-intrusive and really automated operation and maintenance, because you don't want some poor guy going out there to adjust the system every other day. Okay? And there's a couple of approaches currently. Robotics actually has a bunch of things. A lot of them are vision and laser rangefinder based, LiDARs, things like that. Of course, they're not low cost, not low weight, not low computation, but really have high accuracy. So that's the accuracy we want to get to sometimes. Radio signal strength, using radio signal strength to do fingerprinting or do ranging, they're really not accurate. There's other type of things, time arrival, angle arrival, there's ultrasonic, there's hybrid techniques, but they're all lacking in some way or another. So all these approaches, what they usually do is actually they use some type of radio or some other things to get your measurement of distance. Then using that distance measurement, put it in some algorithm, and outcome is some type of location. So what you actually are missing is, because of a few stages here, you're actually missing, losing information at each stage. So what we came up with, it's a system we call PANDA, Physical Arrangement of Network Devices through Ambient Sound Awareness. So the reason is that there's a lot of ambient sound in these type of environments. So the PANDA system uses basically one microphone and the network connection. You have one device and a bunch of other devices, and a bunch of ambient sound. By ambient sound, what I mean is things like coughing, things like door slamming, things like a phone ring, claps, and all those other things. Now, what we don't know are the locations of all these devices. So what we don't know is the locations of all these devices, and that's what we want to know. But we also don't know the location for all these ambient sounds. So we built a system that handles this. Basically, we use a microphone, capture the sound, do some framing, extract the impulsive sounds from that, do a time difference of arrival estimation, do some filtering, and then finally get the arrangement all in one shot. So what does the system do? Basically, you have two devices. You have some sound source. And what you want to find is the distance between device A and device B. But what you can measure is actually the time difference of arrival between the two devices of a common sound. So what that means is that the difference is actually less than or equal to the true distance, right? So for each sound, each ambient sound, what you will get is actually a lower bound of the distance between A and B. Now that's actually a problem, because when you have a lower bound and no upper bound, it's really hard to make an estimation. So what you will have then is, well, there isn't just one sound, of course. There are more than one sound. The sound source 2 may actually get you closer. Of course, some may actually get you further away. So, but eventually, can we just take the highest lower bound, the maximum of the lower bound, because it will eventually approach this actual distance. But immediately there's a problem here, right? Because you notice that the location of the sound actually matters a whole lot. It's really good if it actually lines up with device A and device B, and pretty useless if it doesn't. So that's kind of pointless. Basically, if you rely on ambient sound, they will have to happen to line up with two of your devices to make this all work. So that will pretty much never happen, right? But that's only if you have two devices. But you realize that if you have more than two devices, one sound will eventually line up with two of the other devices, right? If you have 4 devices here, even though that sound source S wasn't able to contribute to A and B, but it was able to contribute to AC, AD, and CB. And with just the estimation of 2 devices, we can actually improve for the entire system. We can estimate everything based off one measure location. So eventually we can build these things up. And of course, we did some experiments to actually test these things. So we took over a meeting room over there in Silicon Valley. It's an 8 by 6 meter meeting room. We placed 8 nodes on the tables. We generated sound at 100 locations. Basically, put a speaker 100 locations on those grid in the room. And we use a certain ambient sound for our experiments. Basically, we use 4 different types of sound: coughing, conversation, music, and music. 2 different types of music. So why did we choose coughing? Well, coughing is a very common sound that people have in the environment today, or sometimes even in the hospital environment, coughing is very common. And another reason is actually we did these experiments in winter, and one of our colleagues just happened to come down with the flu. So of course, our immediate reaction is to lock him up in an echoless room to record his cough for 5 hours, actually. So he was appreciative of that. But of course, you say, well, that's just one sample. It doesn't really, it can't really be expanded to other people. But let me assure you, he did infect other people. So we did have 2 males, 4 females that got infected, and we locked them up too. It's all very humane. So the first thing we have to do is actually, from these events, once we overhear these ambient sounds, we have to extract the impulsive sounds from that. Oops. So, you know, it's nice and easily, so coughing is actually a very nice sound that can really be, the impulse can really be extracted quite easily. And of course, there's other sound.
I live in a bad neighborhood. At least that's what people said about it. Cottage Grove Avenue, said a friend. That's a bad neighborhood.
I hope that's not where you live. I really should pick a more positive soundbite. But anyways, speech is actually a little more difficult, as you see, because the tones are harder to recognize. But of course, there's music too. One of my students, huge Michael Jackson fan. I don't know why. But you see these impulses are really easy to pick up, and it's very nice if you have these type of very...
In restless dreams I walked alone, narrow streets of cobblestone.
So you see, like, the hippie type music isn't really great for our system because the impulses aren't very distinct. But still, even in these type of very soft music, you still see some impulses were extracted. So on average, we have 1 event per cough. For other type of things, we have about 1 event a second. So that's still okay-ish. And we put that all into our system, and we get, maybe not. Yes. we get this. Different type of sound source generated at different locations. You see the distance between the estimated, which is the estimated, which is the pluses, is getting closer to the true is the pluses. The estimated is little diamonds, and they're getting closer and closer together. And as you increase the sound sources, the estimation gets better. And this is sort of the error graph that you see. Eventually, it settles fairly quickly after only 6 sound sources. And then just based on the different noise available, it eventually goes up and down. The average accuracy is about lower than 20 centimeters. So that's pretty good. And of course, sometimes even after it settles, it goes back up a little bit. In this instance, I believe there was a big truck that went right around the outside of our little meeting room. The whole thing was shaking. So the echoes confuse our system a bit. But really what we want to know is actually, well, if once we get these are the location of the devices that we want to measure. So once we get this, can we use this information for our for other needs, like localizing the sound sources, right? Because we also want to localize the sound sources, which are the flying helicopters. So this is a graph that shows how accurate the sound source localization is. Take a note of so the vertical is a cumulative distribution function, basically what percentage is within this error. Horizontal is amount of error. So if you actually look at if we can tolerate half a meter error, the blue line is the Panda system, which is somewhere around 80% is within half a meter error. Roughly somewhere above 90% is within a meter error. And that's really comparable to the brown line, which is a manual survey based on actual physical measurements. So that's actually pretty close, so we're pretty happy about that. So this is based on randomly chosen 500 sources, analyzed after steady state. Basically, helicopter has landed a little bit and things are flying around for a little while. We do achieve less than half a meters, under 80% of the time. So that's not too bad. So this thing really shows that we have a proof of concept that uses ambient sound for physical arrangements. We have lower than 20 centimeter, better than 20 centimeter accuracy. And even in bias distribution, which I unfortunately did not show you, we can get better than half a meter accuracy. So what does this mean for the future? So in the future,
the Milky Way galaxy contains a mind-boggling number of stars, anything up to 400 billion. Now that's 4 times the number of people who have ever lived. Sci-fi has always assumed that we'll explore the galaxy in manned spacecraft. But with as many as 400 billion star systems to visit? No way! Houston, we have a problem. Dr. Pei Zhang of the Carnegie Mellon University is the brains behind a new generation of robotic drones, or swarm bots.
They're just like toy helicopters in the sense that they're cheap. The difference is these things are somewhat smart and they have sensors.
What kind of sensors on these things?
So you can put any sensors you want. So there's you can sense temperature, you can sense light, you can actually take pictures.
And they can do more than that. They share information using onboard radios.
The radios will say, here's a wall, stay away from this place. And to sense the wall, it just hits the wall.
Ah, so one of them learns and then tells the others, watch out.
Exactly, it's like an ant. They leave a pheromone trail and the rest can follow.
Can you imagine millions of these things being sent into outer space?
Well, certainly, space is a very hostile environment. A few of these things can get destroyed, but the entire system is still working.
So instead of sending Captain Kirk into outer space, which is wasteful, we just send billions of these things that are very cheap, expendable, and intelligent.
Captain Kirk might not be too happy, but sure.
I like him. He can make everything sound exciting. But so, I guess what have we learned? Well, we have learned physicists think helicopter can fly in space. But it's sort of idea using swarm network in the exploration, I guess. But collaboration in multiple devices can really increase the capability of the system, even with really minimalistic nodes. Mobility are really different. Don't think mobility is the same. Zebras are very different than helicopters. And sharing the physical context can be used alongside the virtual context to enhance these system capabilities. And with that, I'll take questions. Oh, that was so clear. Yes.
Do you have any feel for how many or how well your devices can do in noise-polluted environments? So pictures of fire, for example. So I'm imagining here crackling fire noise everywhere, trying to figure out where you are. What does that kind of background noise do to your localization?
So the background noise actually helps because they actually, if you're talking about crackling a fire, it's actually crackling at one location. So we actually use that as an ambient source for localization. However, you're talking about something that's maybe like a refrigerator hum. That's just a terrible thing for us. That way, our system handles that by raising the noise floor. So it actually looks at the impulses above that noise floor. So if you have, say, a huge party, it's going to be a slight problem. But we have actually demo this thing in the conference hall, where a demo session at a conference hall where there's a lot of people and very noisy, and it still works if you make sound hard enough. So the system is definitely able to handle that. Another type of system is a very noisy system where there's so many impulsive sounds that overwhelms the system. What the system does in that situation is it just throws everything else away. Right? It takes one process and just ignores everything else. If two sounds happen at the same time, that's also a problem. Right? In that case, it measures the distance. It's too far off. It just cuts it out as an outlier. So it does handle those things.
How about for open air sensing? Have you tried anything there?
What do you mean open air sensing?
Outside?
Oh, outside. So these helicopters barely even flies with air conditioning on. Outside is not the most best thing for these platforms. But the research sort of is focused on the algorithm side of things, right? So the platform can be swapped out to something more, something better, perhaps the robotics folks can build. But for us, since we see this as platform independent, but just as our test bed, it's not designed for outdoors.
So for the algorithm independent platform, does it work better? How does it work in open air?
It works much better in open air because you won't have the, for example, sound. You won't have the echoes that's caused by all of these walls and stuff. And for the radio too, you won't have the echoes. You won't have the multipath. So everything works better outdoors.
How long does it take to sort of get a map of an area?
So the time for a map, we haven't gotten to the map stage yet. We're working on that right now, actually, since we already have a localization and navigation, which I didn't talk about. But to map an environment, we have some a preliminary data from a supermarket. We actually put these devices, we didn't fly them, we just put them on carts and push them around in a live supermarket. The guy was really nice for us to do that already. I think flying them will be pushing it a little bit. So we did that in a supermarket, and we pushed around about equivalent of 100 people walking around for an hour. And we were able to get the sort of a path, the traversable path inside the supermarket. So that's at least one sample point. So within an hour, right, we get a really, really nice path of everything. But even before that, after what looks like 5 minutes worth of data from these devices, we're able to get a rough path. That doesn't mean there's no collisions, but as you see, we deal with collisions fairly well.
Did you think about other ways to do the localization?
Yeah, so we actually have 2 ways to do localization. Sound is just one way. We have a radio for time of flight measurements. That's
to read the difference of time of arrival of Wi-Fi signal or radio signal between the acoustic signals.
We actually we thought about that too. So we have a time arrival for the radio signal. We even just use that to measure the distance, and we actually found out outdoors it works great, right? Earlier I mentioned about outdoors, indoors. Outdoors it works great. You can get about 1 meter accuracy from time of flight radios. Indoors, unfortunately, because of multipath and everything, so these radios, they measure the time of flight of the packets. They don't measure the distance. So once you have a multipath effect, they measure the strongest path. They measure the nice paths you have, which means for our results, we were able to get roughly about 20-meter error from roughly within 5 meters. So that's a multipath effect, if you will. So that's why we couldn't really rely on the radios. For the sound, we did not actually look at distance, right? We look at sort of probabilistic distribution and look at one of the edge of the distance and try to estimate that edge. So that's why we're able to get somewhat of a more accurate measurement. But yeah, that's probably, yeah.
Would it be useful to have the capability for a landed node to deliberately make a sound for others to hear?
So we thought about that. That's probably make the system a lot easier, right? So yes, and in fact, we do have a way to make sound. Spin the blade up a little bit. But we really haven't tested that yet. But that's a really interesting idea. I think some people in the cell phone, using cell phones have tried that because there's a speaker right there. And they have generated like sounds that are easy to interpret, impulsive sounds that are really distinct. And that's definitely a way to go. Except that it's slightly annoying every time it's your cell phone trying to generate something. So some other groups have tried to sounds that are not annoying, like slamming a door, people coughing, clapping. So those sounds aren't as annoying as like a screech or something like that. But yeah, that's an idea that's out there.
All the examples you showed were producing a 2-dimensional map. And these, would you need more microphones on each helicopter to do 3D? What kinds of 3D options are there?
So 3D is a little more difficult. These things are certainly, all the algorithms are extendable into 3D. Right? 2D are just faster in that sense. With 3D, yes, you need more microphones, you need more sound sources. That means a longer delay. But everything is extendable to that. Yep.
Is the overhead to compute the localization?
Compute localization overhead is not small. We do compare with pretty much all the nodes right now. So it's a very brute force way of trying to do these things. Everything is sent to a central server, and right now using MATLAB flow, it's able to actually calculate this within, I think, 10 seconds. So I don't expect the helicopter to do this all by itself, but.
I don't put a mobile phone, for example, an Android phone on the helicopter to do the computation.
Yeah, so there could certainly be a heterogeneous capability for these devices, right? Some could be heavier in the sense it's just bigger. We also look at sometimes you can use some of these what they call the pack bots that the Army has. So you have a pack bot that runs around that, one of the things that helicopter cannot do is open doors. So these things can ram the doors open, put in the helicopters, and provide a computational platform. And although those things can get stuck, but the helicopter is sort of they balance each other out in that sense. So yes, that's one really way we're looking into.
How possible would it be to make something like a disposable helicopter, like $5 at the most, send them into a burning building? You don't actually care that they get burned up. In fact, you intend for them to be great.
So if you actually look at the robotics platform, usually we're talking about low-cost platform in the range of $1,000 or something. So these things are designed to be disposable in that sense. If you just look at the parts cost, if you exclude the radio, that's an expensive part. You're talking about $20 per device. So we're getting down to that range, although perhaps we're even at that range if we're talking about 10,000 manufacturing, 10,000 of them, right? It's mostly a volume thing at that point. The radio is expensive only because it's a one source type of thing. There's no competitors yet, but I don't see why that price doesn't go down in the future. But because we don't have like the array of sensors that's required for like single robots, because it's multiple, and because we don't care about collisions, it's actually around that's sort of the things we're trying to accomplish, the disposable aspect.
Video surveillance using the SensorFly, sort of a CMOS camera on it and relaying.
Yeah, so the SensorFlies do have a little attachments in the front. They can, so the original idea is that you can put different type of sensors on there. The sensor that's, well, everybody asks is the vision sensor. To do full video processing is beyond what these SensorFlies can do. But what they do now is, what we want them to do now is actually just take a picture within the system of process, try to figure out if there's something possibly of interest. So it's looking for like contrast. So just very simple, 1980s computer vision type of things, right? Using those, distributed sort of a majority voting type of way, we say, okay, now these things are looking at the same location. There's probably something interesting. Now let's send a video feed to the base station. Right? So we're not doing high-end processing. We're just doing a low-level sort of majority vote type of things, and then human verification. Yeah.
Like on these, if I have the radio on and they're like, what's the maximum they can go without?
So energy consumption, you can think of all the electronic parts as consuming 0 as long as the motor is on. Right? The motor is our highest energy consumer by far. With the motor on, the flight time is only about 5 minutes right now. Now we see that with tweaking and things like it can extend to 10 minutes, but there's a lot of tweaking if you have 100 nodes, right? So what we foresee is actually they fly sometimes, and then do all the processing, all the sensing will land it. And once we land it, then we have a long time. It's sort of maybe like if you have everything on, no power management, no nothing, it's about an hour runtime.
What is the algorithm to detect the time of arrival?
That is actually enclosed in the radio. So basically what they do is they send a little chirp. The chirp gets received by the other radio. They send the chirp back along with the processing time. So it's sort of a very simple round trip time of flight type of thing. Okay. Thank you very much.